Ancient stonework in Bolivia fits together with a precision that defies logic. The site of Puma Punku presents an impossible puzzle, one where massive blocks of rock interlock with seams tighter than a razor blade, as if machined by modern tools rather than shaped by ancient hands. By the end of this exploration, you will understand why this single site forces us to reconsider everything we think we know about early human innovation. How did builders thousands of years ago achieve a level of geometric perfection that still stumps engineers today? And what forgotten knowledge does their work imply? This journey examines the hard evidence, from eerily clean cuts to complex modular designs, searching for answers in a past that refuses to stay in its expected box. What does it mean when the artifacts left behind seem to outpace the history written about them? The sheer flatness of these surfaces is the first clue that something extraordinary happened here. It is not merely that the stones are smooth, but that they are flat across distances that should be impossible for ancient builders to verify. Imagine trying to make two separate tables perfectly level with each other using only a piece of string and a rock. Now scale that challenge up to a stone block weighing many tons, and you begin to grasp the magnitude of the task. At Puma Punku, the surfaces of these massive andesite blocks are planar, meaning they are perfectly flat, not just to the naked eye, but to a tolerance measured in fractions of a millimeter. This is a level of precision we associate with machine shops, not with a culture working over 1,000 years ago. This precision becomes even more baffling when you examine how the stones connect. They were crafted using a principle called modular construction. Each block is not a standalone monument, but a component, designed to interlock with others like pieces in a vast three-dimensional puzzle. The most famous are the H-shaped blocks, which feature complex notches, grooves, and protrusions that slot together with neighboring stones. The seams where they meet are so impeccably tight that, as many observers have noted, you cannot fit the blade of a razor between them. This is not a poetic exaggeration, it is a physical description of the fit. Such a feat requires more than careful craftsmanship. It demands a master plan, a set of standardized measurements, and an execution so consistent that every single component matches its intended partner perfectly, every single time. Materials scientists who have studied the site point out what this implies. Achieving surfaces this flat and edges this sharp on a stone as hard as andesite would be incredibly difficult with simple hand tools. There are no telltale marks from pounding stones, no grooves from repeated grinding. The cuts are clean, the corners are often perfect right angles. This suggests the use of guided tools, something that could hold a cutting edge in a fixed position to ensure a straight, uniform cut across the entire length of the block. Think of the difference between drawing a straight line freehand and using a ruler. One method relies on shaky human skill, the other on a guiding principle that enforces precision. The uniformity is staggering. We are not looking at one or two perfectly cut stones that might be lucky anomalies. There are hundreds of these blocks scattered across the site, all displaying the same exacting standards. It is as if every stonecutter had access to the same blueprint and the same advanced toolkit. A relatable modern analogy is a granite countertop in a kitchen. That smooth, seamless surface is created today using industrial saws with diamond-tipped blades, guided by lasers and computers to ensure absolute precision. The stones of Puma Punku invite a haunting comparison. They look as if they were produced by a similar, if not identical, process, so we are left with a reflective puzzle. How did these builders achieve such flawless consistency without the measurement tools we consider fundamental, like precision levels, calipers, or even standardized rulers? The answer seems to lie not just in their hands, but in their understanding of the material itself, forcing us to look closer at the rock they chose to shape. This choice of material is a mystery in itself. The builders of Puma Punku did not select an easy medium. They worked primarily with andesite, a volcanic rock forged in immense heat and pressure, with a hardness approaching that of quartz. To put that into a modern context, it is harder than most steels. Granite, also present at the site, presents a similar challenge, being famously tough and resistant to wear. This was a deliberate selection of the most durable, most difficult stone available, not a convenient or soft alternative like sandstone or limestone. The very nature of these materials resists the basic actions of carving and shaping. A simple stone hammer striking a block of andesite would more likely chip or shatter the surface than create a clean, controlled cut. A copper chisel, the hardest metal commonly available in the region at the time, would simply bend or blunt against it. The physics are unforgiving. To cut a hard material, you need a tool that is even harder, or you need a completely different approach. This presents a glaring problem for the conventional historical timeline. There is no evidence that the Tiwanaku culture, to whom the site is traditionally attributed, possessed hardened iron or steel tools, nor industrial diamond-tipped blades. So how did they do it? Geologists who study ancient stonework point to a technique called abrasive cutting. This involves using a substance like quartz sand, which is harder than andesite, as a grinding agent. By dragging a piece of wood or a rope back and forth across the stone with the sand and water in between, you can slowly, painstakingly wear a groove. It is a process of subtraction by friction, not impact. While this method is theoretically possible, it raises immense practical questions when applied to the scale and precision seen at Puma Punku. Creating one flat surface this way on a small scale is a monumental task of labor and time. Creating hundreds of them, all perfectly identical, with intricate interlocking joints and razor-sharp edges, becomes a logistical puzzle of almost absurd proportions. Modern experimenters attempting to replicate these results using only tools and methods believed to be available at the time have consistently fallen short. They can produce rough shapes but never the machine-like perfection, the flawless planar surfaces and tight seams that define the ruins. The sheer hardness of the stone acts as a silent witness, testifying that the methods we assume were used may not have been sufficient. This forces a reflective question about the builders themselves. What drove them to choose such a punishing material? It speaks to an intention for permanence, a statement meant to last for ages. But it also implies a profound confidence, a certainty that they possessed the knowledge and capability to master it. Their choice tells us they were not intimidated by the challenge, they were equipped for it. This gap between the presumed tools and the achieved results is where the true mystery deepens, pushing us to look beyond simple hammers and chisels toward something far more sophisticated. The silence of the stones is perhaps their loudest statement. On block after block at Puma Punku, you encounter surfaces that are not just smooth but eerily unmarked. In a typical ancient quarry or workshop, you would expect to find evidence of the struggle, the story of creation told in the stone itself. Chisel grooves from where a mason guided his tool, percussion pits from repeated hammer blows, or striations from a saw dragged back and forth. These are the fingerprints of the artisan left behind for us to read. At Puma Punku, those fingerprints are missing. Many of the most precisely finished slabs show no such signs of manual tooling at all. It is as if the stones were not carved in the conventional sense, but somehow formed or finished by a process that left no trace of its method. This puzzling absence turns the site into an archaeological detective story where the lack of evidence becomes the most compelling clue of all. This leads to a critical question about the manufacturing process. How do you shape incredibly hard stone without leaving the telltale marks of hammering? chiseling, or sawing. Forensic stonemasons and materials experts who have examined the site point toward a technique that relies on abrasion, not impact. The theory suggests a process of grinding and lapping. Imagine using a large, perfectly flat stone slab as a reference surface. A slurry of abrasive sand, which contains quartz harder than the andesite, mixed with water, would be spread between the reference slab and the block being shaped. By moving the block in a precise, repetitive motion, the abrasive particles would slowly, molecule by molecule, wear the surface down to a perfect plane. This method could explain the planar surfaces, as the reference slab ensures flatness, and the abrasive does the cutting without leaving gouges from a chisel's edge. The evidence for this becomes even more striking on specific features. Some blocks at Puma Punku contain drilled holes. These are not rough, conical depressions made by a handheld drill wobbling under pressure. They are perfectly cylindrical, with smooth, parallel walls that run straight into the stone. Creating such a feature with a simple bow drill and a copper tip is virtually impossible on this material. The copper would deform long before the andesite gave way. A cylindrical hole of this quality suggests the use of a tube-like drill, perhaps made of a harder material, rotating at a consistent speed with a steady feed of abrasive slurry. The finish inside these holes mirrors the finish on the flat surfaces, clean and uniform. A powerful contrast can be seen in other ancient marvels. The unfinished obelisks in the Egyptian quarries at Aswan, for instance, clearly show the marks of their creation. Workers used balls of dolerite, a hard stone, to pound channels around the granite, leaving unmistakable pockmarks and fracture lines. You can see the labor, the technique, the step-by-step process frozen in time. At Puma Punku, that visible process is absent. The stones present only the final, flawless product. This raises a reflective and almost philosophical question. If the builders used known methods, why would they go to such extraordinary lengths to meticulously remove every single tool mark, polishing them away to a mirror-like finish on some slabs? Or more intriguingly, were the tools themselves so advanced, so different from anything we assume they had, that they simply did not leave the kinds of marks we are looking for? This absence does not point to a lack of skill, but rather to a technology or a refinement of process that we have yet to fully comprehend. The stones were not just built, they were finished with an intention that hides their own origins. This geometric complexity transforms the stones from simple blocks into components of a machine. The most iconic forms at Puma Punku are the H-shaped blocks, but that name barely scratches the surface of their design. Each one is a masterpiece of three-dimensional engineering, featuring a central recess flanked by two protruding tabs, all carved from a single, unforgiving piece of andesite. The magic is not in the shape itself, but in how these shapes were meant to fit together. The tabs of one block would slot perfectly into the recesses of another, while the central channel might accept a separate slab or beam. This creates a mortise and tenon joint, a classic woodworking technique, executed here in stone with a precision that defies the material's nature, but the complexity goes deeper. Some blocks feature notches cut at precise angles, others have T-shaped grooves, and some have what appear to be dovetail joints, all designed to interlock on multiple planes, not just from the side but from above and below as well. This is the principle of ashlar masonry, where stones are cut to fit together without mortar, taken to a level of sophistication that feels anachronistic. The joints themselves become the structure's strength. In a region prone to seismic activity, this interlocking design is nothing short of genius. An earthquake sends lateral forces, shaking a building from side to side. A wall held together with simple gravity or weak mortar would crumble, but a wall built from these interlocking blocks behaves differently. The complex geometry turns the entire assembly into a unified, flexible matrix. As forces push and pull, the tabs and recesses transfer stress throughout the network, allowing the structure to sway and settle without collapsing. It is a seismic dampening system carved directly into the bones of the building. Modern structural engineers who analyze these forms express genuine admiration, noting that such a design requires not just skilled craftsmanship, but advanced foresight. You cannot carve these blocks by eye and hope they fit. Each one is a piece of a grand three-dimensional puzzle. This implies the existence of a master plan, a detailed set of instructions or a scale model that guided every cut. The geometric consistency across hundreds of damaged components suggests they were working from a standardized system, a kind of ancient metric or module. A powerful analogy is to look at a modern machine like an engine. Inside, you find gears with specific teeth, pistons with exact tolerances, and shafts with keyways. Each part is useless alone, but when manufactured to a common blueprint, they assemble into a functioning whole. The stones of Puma Punku evoke that same feeling. They look less like traditional building blocks and more like precision-engineered parts, prefabricated for assembly into a larger, perhaps unimaginably grand architectural complex. This leads to a reflective and haunting possibility. The scattered ruins we see today may not be a destroyed building, but a delivery yard of components for a structure that was never finished, or one that was dismantled by a cataclysm we no longer understand. What kind of mind conceives of architecture in this way, not as stacking stones, but as assembling a monolithic machine from stone components? The geometry is a silent language, and it speaks of a knowledge base that encompassed advanced mathematics, structural physics, and a vision for permanence that we are only now beginning to decode. Scattered among the ruins are small, silent witnesses to a forgotten technology. On several of the massive andesite slabs at Puma Punku, you can find perfectly circular holes and narrow, straight channels that look as if they were bored into the stone by a machine. These are not rough, irregular depressions. They are precise, cylindrical ports, often with smooth, parallel walls that plunge deep into the rock. A simple hand-powered drill, a reed spun between the palms with some abrasive sand, could never achieve this result on a material as hard as andesite. The sand would wear away long before the stone yielded such a clean, uniform bore. This is a fundamental clue because hole-making is a cornerstone of machining, the process of shaping a material by removing parts of it in a controlled way. To create a feature like this, you need more than patience. You need a stable, rotary cutting action with consistent pressure. Archaeologists who specialize in ancient manufacturing techniques note that some of these holes are remarkably consistent in both diameter and depth. This uniformity points directly to the use of a rigid apparatus, something that could hold a drill bit perfectly steady and rotate it at a constant speed. The most plausible method for achieving this is called tube drilling or core drilling. Imagine a hollow tube, perhaps made of copper or even a harder stone, attached to a spindle. As the tube is rotated, an abrasive slurry of quartz, sand, and water is fed into the contact point. The tube does not cut the stone in the way a modern drill bit does. Instead, it grinds away a circular groove. As the drilling continues, it leaves behind a solid stone core inside the tube and creates a perfect cylindrical hole in the block. This technique requires sustained force and stability, something far beyond a person simply twisting a stick back and forth. The evidence becomes even more compelling when you see where these holes are placed. Some are bored at precise angles into the sides of blocks, or in positions that would be incredibly difficult to reach with a handheld tool while maintaining the necessary downward pressure and rotational speed. This suggests the use of a frame or a drill press-like apparatus to guide the tool. A striking example is found on a famous block often called the keystone. This fractured slab is riddled with an array of these perfectly formed ports, arranged in symmetrical patterns. the precision of their placement is so exact that it rules out chance or freehand work. Some researchers have theorized these ports could have had a functional purpose, perhaps as anchor points for metal clamps or as part of a complex hydraulic system for the site. Others see a symbolic or architectural design. Regardless of their ultimate use, their existence forces a difficult question: what powered these drills? Human muscle alone, even with a bow to spin the drill, struggles to provide the consistent torque and downforce needed to tube drill through andesite. Could it have been a larger mechanical advantage system, like a weighted lever or even a simple lathe? And more perplexingly, what were the drill bits themselves made from? To guide the abrasive slurry without deforming, the tube would need to be made of a material rigid enough to maintain its circular shape under tremendous stress. The presence of these features is a quiet but powerful argument. It hints at mechanical aids, at tools and processes that provided a level of control we do not typically associate with that era. These are not the marks of primitive effort, they are the fingerprints of applied mechanics, a silent testament to a workshop where stone was not just carved but machined. The most controversial explanation for these impossible stones lies in the idea of a forgotten chapter in human history. This theory suggests the builders of Puma Punku possessed a form of advanced technology that has since been lost to time, knowledge that rivaled or even surpassed what we typically attribute to that ancient era. It is a realm of speculative history, one that moves beyond conventional tools to consider the possibility of powered machinery, sonic devices, or techniques we simply no longer understand. Proponents of this view point directly to the craftsmanship itself as the primary evidence, arguing that the machine-like precision is the artifact of a machine-based process. They ask a fundamental question: if the tools we believe they had are insufficient, what tools did they actually use? Some researchers exploring alternative histories look to local Andean legends for clues, particularly the stories of Viracocha. In these traditions, Viracocha is described as a great teacher, a bearded figure who arrived after a period of great upheaval, bringing with him knowledge of agriculture, architecture, and social order before departing across the sea. To some, this is not merely a myth, but a cultural memory of contact with a more advanced group, or perhaps a remnant of a prior, sophisticated civilization that was largely lost. The theory extends to a global pattern, pointing to other so-called out-of-place artifacts like the massive, precisely cut blocks at Baalbek in Lebanon or the mysterious vitrified stone forts in Scotland. These sites, scattered across the world, each present their own engineering puzzles that seem to defy their accepted timelines, collectively suggesting that the story of human technological progress may not be a simple, linear climb, but a series of peaks and valleys with knowledge rising, falling, and sometimes disappearing entirely. One specific technological idea that emerges is the concept of sonic or vibrational cutting. The theory proposes that if you can find the resonant frequency of a particular stone, you could use sound waves to create intense vibrations along a precise line, causing the rock to fracture cleanly with minimal effort. This is not pure fantasy. Modern diamond wire saws and ultrasonic cutters use similar principles of focused energy to slice through hard materials. The absence of tool marks on the Puma Punku stones could be explained if the stone was not cut, but persuaded to separate along a predetermined plane. This line of thinking forces a crucial distinction. There is a wide gap between the fringe idea of ancient aliens or supernatural intervention and the genuine, unresolved mystery of the method. Mainstream archaeology readily admits it lacks a definitive explanation for the toolset used. The lost technology theory, in its more grounded forms, is an attempt to fill that explanatory void with human ingenuity rather than extraterrestrial help. It asks us to consider that our ancestors might have discovered principles of physics and material science that we have since overlooked or forgotten. perhaps because the knowledge was held by a small, specialized group and never widely disseminated. This leads to the theory's greatest challenge, the question of evidence. If such advanced technology existed, why is there no direct, unambiguous trace of it elsewhere? Where are the workshops, the failed experiments, the tool fragments? Proponents argue that time is a powerful eraser, that a cataclysm or a long dark age could scatter and bury such evidence beyond recovery. They also suggest that perhaps we are looking for the wrong things, searching for metal gears when the technology might have been based on sound, water, or leveraged stone. Ultimately, this theory is less about proving a specific device existed and more about expanding our perspective on human capability. It pushes us to look more deeply at the cultural and intellectual context of the builders themselves. What worldview, what understanding of their environment could have led to such an elegant and formidable solution to working stone? The stones stand as a permanent question mark, inviting us to wonder not just how they were built, but what kind of minds conceived of building in such a way. To understand the true depth of the puzzle, we must meet the people history books credit with its creation. The Tiwanaku Empire was a dominant force in the Andes, its influence stretching from what is now Bolivia into Peru and Chile for centuries, roughly from 500 to 1000 AD. This was a sophisticated theocratic state, a society governed by spiritual leaders who wielded immense power. Archaeologists describe Tiwanaku as a marvel of organization, a civilization that mastered its harsh high-altitude environment through ingenious raised field agriculture, developed complex social hierarchies, and built a capital city centered around monumental architecture and celestial observation. Their main ceremonial complex, just a short distance from Puma Punku, is a testament to their skill. Here we find the Akapana Pyramid, the Kalasasaya Temple enclosure with its iconic standing stones, and the massive sandstone blocks that form the walls of the Putuni complex. The stonework here is undeniably impressive, featuring large, finely fitted stones that have withstood centuries of earthquakes. Yet, to a trained eye, there is a distinct and telling difference. The stones at the main Tiwanaku site show the marks of their making. You can see the pecking and grinding, the patient work of stone against stone. The joints, while tight, are not the razor-thin, machined seams of Puma Punku. The surfaces, while smooth, are not the flawless planes found just over the ridge. This contrast is crucial. It establishes a baseline for what Tiwanaku stonemasons were known to achieve with their documented toolkit of bronze chisels, stone hammers, and abrasive sand. Their methods were advanced for their time, but they were fundamentally manual. Consider the famous Gateway of the Sun, a single carved block of andesite that stands as a masterpiece of Tiwanaku iconography. The intricate depiction of the central deity, often called Viracocha, surrounded by winged attendants, is a profound artistic and symbolic achievement. Technically, however, its creation involved carving reliefs into the surface of a monolith, a different challenge altogether from fabricating multiple, interlocking geometric components with engineering precision. The gateway shows us their artistry and spiritual vision, but it does not demonstrate the same kind of modular, machined construction. This leads to the immense logistical question: how did they even get the stones to the site? The andesite blocks were quarried from a mountain over 50 miles away, across rugged terrain and a vast lake plain. Transporting multi-ton stones such a distance without the wheel or draft animals is a staggering achievement in itself, speaking to a highly mobilized and coordinated society. It proves they could move the stone, but it does not explain how they shaped it with such otherworldly finesse. So we are presented with a fascinating possibility within the mainstream framework. Could the Tiwanaku have harbored a secret, a specialized guild of master builders whose techniques were so advanced, so protected, that they left no trace in the broader archaeological record? Perhaps Puma Punku was their ultimate workshop, a place where this elite group applied a lost subset of knowledge, a hyper-refined version of abrasive technology combined with sophisticated measuring and guiding apparatuses that simply did not survive the empire's eventual decline. This view accepts the Tiwanaku as the builders, but suggests their full capabilities have been underestimated. By grounding the mystery in the solid history of this remarkable civilization, the anomaly at Puma Punku becomes not less strange but more focused. It asks us to look closer at a gap between what we know they did and what they seemingly could do, a gap that holds the key to a forgotten school of ancient engineering. The journey of the stone itself is a monumental story. Before a single perfect cut was made, these colossal blocks of andesite had to travel an epic distance, from the quarries on the distant slopes of Mount Capia, over 50 miles across the harsh Altiplano to the shores of Lake Titicaca, and then finally up to the high-altitude site of Puma Punku. This was not a simple delivery. It was a staggering feat of logistics that shifts our focus from the finesse of the workshop to the raw power and coordination of an entire society. We are talking about moving stones that engineers estimate weighed well over 100 tons each, in an environment where the air is thin, the terrain is unforgiving, and the wheel was unknown, as were large draft animals like oxen or horses. The sheer physical challenge is almost incomprehensible. To move a single one of these blocks today would require heavy cranes and flatbed trucks, a convoy of modern machinery. The builders had only human muscle, rope, and ingenuity. Experts in ancient engineering propose several methods that could have been used, each a testament to clever problem-solving. The most likely technique involved a combination of log rollers and sledges. Imagine a massive stone block carefully levered onto a wooden sledge. This sledge would then be pulled, likely by teams of hundreds of workers using thick ropes made from llama hide or plant fibers, across a path of rolling logs laid out in front of it. As the sledge moved forward, workers behind would pick up the freed logs and rush them to the front, creating a continuous track. On inclines, the challenge multiplied, requiring elaborate systems of levers and counterweights. Another theory suggests they may have used the region's clay-rich soil to their advantage, wetting the ground to create a slick, muddy surface that would reduce friction for the sledges. The coordination required for any of these methods is breathtaking. It speaks to a society with a military-like command structure, capable of organizing and sustaining a large labor force for a single, purpose-driven task. This logistical masterpiece raises a crucial practical question about the precision we see. How could you transport a block with intricate, pre-cut joints and razor-sharp edges over 50 miles of rough terrain without chipping or damaging those delicate features? The likely answer points to a sophisticated, multi-stage manufacturing process. It is widely theorized that the stones were only rough cut at the quarry, shaped into oversized blanks that were easier and safer to transport. The final, precise machining, the creation of those perfect planar surfaces and complex interlocking joints, would have been done on site after the grueling journey was complete. Evidence for this exists at the quarries themselves, where unfinished blocks remain, showing the initial stages of shaping but none of the final, flawless finish found at Puma Punku. This separation of labor, quarrying, transport, and precision finishing reveals an advanced understanding of project management. It means the master builders at the site were working with a known quantity, a blank canvas of stone that had already survived the hardest part of its journey. The logistics thus become a bridge between the possible and the impossible. They demonstrate the tangible human power of the Tiwanaku state, its ability to marshal resources and labor on a grand scale. Yet they also protect the mystery of the final craftsmanship. By finishing the stones at their destination, the builders ensured that their most advanced techniques, their true technological secrets, remained within the sanctum of the site itself, hidden from the quarries and the long road home. This careful process makes the final product even more remarkable, a symbol of both immense collective effort and guarded, specialized knowledge. But the stones were not meant to be admired in isolation. Gaze upward and consider that Puma Punku, like so many sacred sites of the ancient world, may have been a bridge between earth and sky. The staggering precision of its construction could have served a purpose far greater than mere architectural stability. It might have been a functional component in a giant stone observatory, a machine for watching the heavens. Archaeoastronomers, scientists who study how ancient cultures understood the stars, have long noted that the broader Tiwanaku complex is rich with celestial alignments. The nearby Kalasasaya temple, for instance, features a grand gateway and monolithic markers that align with the rising sun on the equinoxes and solstices. This reveals a civilization deeply attuned to the cycles of the sun and moon, tracking them with remarkable accuracy to create a sophisticated calendar that governed agriculture and ceremony. The question then becomes, what role did the hyper-precise stonework of Puma Punku play in this cosmic observation? One compelling hypothesis focuses on those flawlessly flat surfaces. A perfectly planar stone, polished to a high sheen, becomes more than a building block. It becomes a potential mirror. Such surfaces could have been used to reflect beams of sunlight or moonlight into specific areas of the complex at precise times of the year, marking celestial events with a dramatic play of light and shadow. The complex geometry of the interlocking blocks might have then served as a three-dimensional diagram, a permanent stone record of astronomical knowledge, encoding the movements of stars or the patterns of constellations in the angles and alignments of its walls. Imagine the winter solstice sunrise, a pivotal moment in the agricultural year. The first golden light crests the distant mountains and strikes the site. Perhaps it illuminated a specific port in one of the H blocks, or cast a shadow that lined up perfectly with a groove in a neighboring slab. That moment, captured in stone, would turn the entire architecture into a celestial clock, its accuracy dependent on the exact placement and angle of every single component. This offers a profound answer to the reflective question of why such exacting work was necessary. If your society's survival depended on knowing precisely when to plant and when to harvest in a harsh climate, and if your spiritual beliefs were woven into the fabric of the cosmos, then your tools for measurement needed to be as perfect as humanly possible. A calendar off by a few days could mean famine. A misaligned temple could mean failing to honor the gods correctly. In this light, the drive for precision was not an artistic whim, it was a cultural imperative. The need for perfect astronomical observation could indeed have been the engine that drove the development of such advanced stone shaping techniques. The site then transforms from a ruined building into a ceremonial instrument, a place where the community gathered to witness the reaffirmation of cosmic order, made visible through the silent, perfect interaction of stone and sunlight. This celestial connection weaves Puma Punku into a broader tapestry of ancient knowledge, suggesting its builders were not just master engineers, but also keen scientists of the sky, seeking to anchor their world in the dependable rhythms of the universe. Yet this precision takes on a new dimension when seen next to other ancient wonders. The world is filled with incredible stonework, from the colossal pyramids of Egypt to the seamless walls of Inca Cuzco and the enigmatic circles of Stonehenge. Each represents a monumental human achievement, a triumph over gravity and material. But a closer, comparative look reveals that Puma Punku stands apart not in scale, but in its fundamental philosophy of construction. Consider the iconic walls of Sacsayhuaman above Cuzco. The Inca are famous for their polygonal masonry, where massive, irregularly shaped stones are fitted together with breathtaking tightness. The process, however, was fundamentally adaptive. Stonemasons would painstakingly shape each unique stone to fit the specific contours of its neighbors, like assembling a three-dimensional jigsaw puzzle. The result is a masterpiece of organic, custom fitting, where every stone is an individual, Puma Punku operates on the opposite principle. Its H-blocks and geometric slabs are not custom fit, they are standardized. They are repeated modular components, each seemingly manufactured to the same exact specifications so that anyone could, in theory, interlock with any other of its type. This is the difference between a tailor making a bespoke suit and a factory producing identical parts for a machine. Both achieve a perfect fit, but the underlying methodology separates a craft from an industry. This distinction becomes even clearer when we examine how these joints were achieved. At all these great sites, from the pyramids to Machu Picchu, the goal was a tight, mortarless fit. The Egyptians achieved it with immense manpower and carefully dressed surfaces, often using leveling beds of sand or gravel. The Inca achieved it through the meticulous shaping of irregular blocks. At Puma Punku, the fit comes from a previously machined precision, where the joints themselves are complex geometric patterns pre-formed into the stone, designed for assembly rather than adaptation. An illustrative contrast lies with the moai of Easter Island. Those awe-inspiring statues are monolithic sculptures, carved to represent figures and then transported. Their power is in their singular, sculpted form. The stones of Puma Punku are rarely sculptural in that sense. They are architectural components. Their power lies in their repeatable, engineered function. This raises a pivotal reflective question for comparative archaeologists. Why did this culture, in this specific place and time, develop this particular, modular approach when others pursued different, equally effective paths? The answer may lie in intention and worldview. The modular system suggests a plan for rapid, perhaps even serial, construction of a complex whose final form was conceived in complete detail before the first stone was cut. It speaks to a culture that thought in terms of systems, templates, and interchangeable parts, a mindset that feels strikingly modern. This comparison does not diminish other ancient wonders, rather, it magnifies the anomaly. It shows us that human ingenuity can arrive at vastly different solutions to similar problems. Puma Punku's solution was one of prefabricated precision, a choice that leaves behind a legacy not just of immense stones, but of a uniquely systematic and engineering-focused mind. Modern attempts to recreate these stones offer a humbling lesson in humility. Skilled stonemasons and experimental archaeologists have dedicated countless hours to answering the central question with their own hands, using only the tools and materials believed to be available to the Tiwanaku. They set up workshops with dolerite hammerstones, copper chisels, wooden frames, and abrasive quartz sand, determined to prove it could be done through sheer human effort and ingenuity. The results are deeply informative, yet they consistently fall short of the ancient standard. A craftsman can, with immense patience, use a copper saw, a flat strip of metal dragged back and forth with sand and water, to slowly groove a block of andesite. Over weeks or months they can cut through it. They can use a bow-driven wooden drill with an abrasive slurry to bore a hole. They can pound away with stone hammers to rough out a shape. The process works in the sense that stone is removed and a form emerges, but the efficiency and, more critically, the precision are nowhere near what we witness at Puma Punku. The modern replicas are visibly cruder, with wavier cut lines, less perfect flatness, and joints that do not achieve that legendary razor blade fit. Breakage is a constant frustration, as the unforgiving andesite often fractures along an unseen fault line, ruining days of work. These experiments reveal a staggering gap in time investment. What a small team of Tiwanaku builders might have accomplished in a season, a modern team using replicated primitive tools might struggle to match in years. This discrepancy points to something crucial. It is not that the task is impossible with simple tools, but that achieving it on the scale and with the consistency found at the site becomes a logistical puzzle of almost absurd proportions. Documentaries and projects like those undertaken for educational parks or television specials clearly show this divide. The replicated H blocks they produce are recognizable in shape, but they lack the machined sharpness, the flawless edges, and the geometric perfection. They look like what they are, handmade approximations. This forces a reflective and important question. If teams of knowledgeable modern artisans, with the advantage of hindsight and modern safety, cannot reliably replicate the precision, what does that tell us about the original technique? It strongly suggests that our model of their toolkit is incomplete. Perhaps they used a more refined version of the abrasive method, with guiding apparatuses that provided unwavering stability. Maybe they employed a different, forgotten principle for cutting or polishing stone that multiplied their effectiveness. These modern efforts do not close the mystery, they widen it. They prove that willpower and basic tools are not enough. You need a system, a technology that bridges the gap between intention and execution. The silent testimony of these failed replicas is as loud as the stones themselves, pointing toward a lost chapter of practical knowledge that we have yet to rediscover. The very definition of a stone block is challenged by another radical idea. What if the builders of Puma Punku did not carve their intricate components but cast them like concrete? This controversial theory suggests that some of these impossibly precise forms were not quarried and machined, but manufactured from a slurry poured into wooden molds. Proponents of the geopolymer hypothesis look past chisels and saws to propose a forgotten chemistry, where ancient engineers created an artificial stone that could be formed into any shape with perfect consistency. Materials scientists who have studied samples from the site point to curious details. Natural andesite, formed under immense volcanic pressure, has a distinct crystalline grain structure that runs in specific directions. Some of the stones at Puma Punku, however, appear to show a more uniform, almost homogeneous composition, lacking that telltale directional grain. Furthermore, the surfaces sometimes exhibit a peculiar texture or tiny bubble-like voids, features more commonly associated with a poured material setting than with stone being cut from a solid mass. The process, as theorized, would have been sophisticated. Builders could have crushed local stone into a fine powder, mixing it with lime derived from burned limestone or shells, and natural alkaline binders possibly made from plant extracts. This thick slurry would be poured into precisely constructed wooden formwork, creating the complex H shapes, channels, and ports in a single step. Once hardened, the resulting block would be a monolithic piece of engineered stone, its geometry limited only by the design of the mold. This method elegantly explains the uniformity and the razor-sharp edges, as a well-made mold produces identical, crisp forms every time. A clear modern parallel is architectural cast stone, a concrete product used today to create ornate window sills, balustrades, and decorative elements that perfectly mimic natural cut stone. The theory, however, faces significant and legitimate criticism from mainstream geologists. Opponents point to the well-documented andesite quarries at Mount Capia, showing clear evidence of extraction. They argue that transporting 50 miles of raw, crushed stone slurry in bulk would be even more logistically challenging than moving solid blocks. Some formulations of geopolymer chemistry also require sustained high heat to activate the binding process, a level of controlled pyrotechnology not clearly evidenced at the site. The debate often centers on a simple but profound question. Are we looking at carved natural rock or brilliantly engineered artificial rock? If casting was used, the achievement shifts from mechanical machining to advanced materials science. It would mean the builders possessed a deep, practical understanding of geochemistry, knowing exactly which local materials to combine to replicate the durability, hardness, and appearance of natural andesite. This knowledge would allow them to overcome the hardest part of stonework, the shaping, by changing the fundamental nature of the material itself during construction. The idea invites a reflective shift in perspective. It asks us to see Puma Punku not as a sculpture garden of massive rocks, but as the world's most durable prefabrication yard, where the very substance of the building was invented alongside its design. Whether the stones are carved or cast, their existence pushes the boundaries of what we believe was possible, standing as a permanent testament to a level of ingenuity that continues to escape our full understanding. The relentless drive for geometric perfection might have sprung from a source deeper than engineering. For the builders, the very act of achieving such flawless stonework could have been a form of worship, a physical prayer etched into the landscape. Anthropologists who study Tiwanaku cosmology describe a world where order was not just practical, it was divine. The heavens moved with predictable, perfect rhythms, and the gods themselves embodied principles of balance and harmony. To replicate that celestial order on earth in stone was to create a sacred bridge, a place where the human realm could touch the divine. In this light, the precision was not merely a technical goal, it was a spiritual imperative. A wavy line or an uneven joint would not just be a structural flaw, it would be a spiritual impurity, a break in the connection to the cosmos. The site itself transforms under this view, from an architectural puzzle into a ritual instrument, a sacred machine designed to operate on a metaphysical level. The immense effort expended, the generations of labor, gains a profound new meaning. This was not to build a palace or a fortress, but to construct a perfect offering, a permanent testament to humanity's desire to align with a higher order. This perspective helps explain a curious aspect of the mystery, the secrecy. If the techniques for achieving this perfection were imbued with sacred power, it makes sense that they would be closely guarded knowledge, restricted to a priestly class or a guild of master builders initiated into the mysteries. The methods themselves might have been considered as holy as the finished product, rituals to be performed only by those with the proper spiritual standing. This creates a compelling parallel with other great religious constructions throughout history. Think of the soaring Gothic cathedrals of medieval Europe. Their staggering height, their intricate stone tracery, and their precise alignment were not merely feats of engineering, they were acts of devotion. The goal was to create a space that inspired awe, that lifted the eyes and the spirit toward heaven, using architectural perfection to glorify God. The craftsmen who built those cathedrals were often members of secretive guilds, protecting their advanced knowledge of geometry and stress distribution as sacred trust. In a similar way, the master builders of Puma Punku may have seen their work as a divine service, where every cut, every polish was a step in a ceremonial practice. This symbolic layer adds a powerful dimension to the technological mystery. Could the intense spiritual desire for perfection have been the very catalyst that drove a technological breakthrough? When a culture's deepest beliefs demand absolute precision, the human mind is pushed to its limits of innovation. The need to create a flawless reflection of the cosmos might have spurred generations of experimentation, leading to the refinement of abrasives, the invention of guiding frames, or the discovery of material properties that we have since forgotten. The stones, then, are not just evidence of how they built, but of why they built. They stand as a permanent record of a philosophy that saw no separation between the spiritual and the material world, where to build with perfect order was to participate in the very structure of the universe itself. The final puzzle of Puma Punku is written in its very destruction. Today, the site is a scene of breathtaking chaos, where multi-ton blocks of andesite lie scattered and shattered, flung across the landscape as if by a giant's hand. This is not a gentle decay from centuries of wind and rain. This is the signature of a single, catastrophic event that tore the complex apart. To walk among these ruins is to witness a frozen moment of immense violence, a key that may unlock what happened to this place and when. Geologists examining the ground tell a story of tremendous force. Layers of sediment, some several feet deep, are packed around and even beneath some of the heaviest stones. This kind of deep, uniform deposition is a classic sign of a massive flood, a sudden deluge of water and mud powerful enough to carry and then drop these colossal weights. Given the site's proximity to the shores of Lake Titicaca, the theory of a cataclysmic flood event, perhaps triggered by a seismic shift in the lake basin or a period of extreme climate change, carries significant weight. Other researchers point to the sheer physics of the scattering. The blocks are not just toppled, they are displaced, some found far from any logical foundation. This pattern also aligns with the direct impact of an earthquake of unimaginable magnitude, one that could liquefy the ground beneath the structures, causing the earth to flow like water and the precision-fitted stones to be thrown into disarray. The destructive power needed to do this to such robust engineering is almost incomprehensible. This adds a profound and tragic layer to the enigma. The very perfection of the stonework makes its shattered state all the more jarring. These blocks were designed to interlock to form a unified, flexible matrix that could withstand seismic stress, yet here they are, broken and scattered. This forces a difficult question: was the force that hit them simply greater than any design could mitigate, or was the complex incomplete, missing key stabilizing elements when disaster struck? Some archaeologists see evidence for both possibilities. The sheer number of finished components, all precisely made but never assembled into a coherent building, suggests the site might have been a workshop or a storage yard when it was destroyed. Alternatively, the scattering is so complete it hints at a deliberate, systematic dismantling, though the motive for such an arduous task remains unclear. An illustrative and haunting clue is found in the way some of the largest blocks are partially buried. They are not resting on the surface, they are embedded in the earth, their lower halves sealed in sediment as if they were dropped into soft mud that later hardened around them. This is a powerful indicator of rapid deposition, exactly what you would expect from a catastrophic flood. The water rushes in, suspends tons of silt, and as it recedes, it drops its heavy load, encasing everything in a thick, preserving layer. This image transforms our understanding of the timeline. It suggests the disaster did not slowly creep up on Puma Punku. It arrived in a single, devastating surge. Reflecting on this, we are reminded of the immense natural forces the builders contended with, living on a high plateau prone to earthquakes and subject to the moods of a vast inland sea. Did their drive for geometric perfection include a form of disaster mitigation, an attempt to create something so orderly it could resist a chaotic world? Or does their scattered work instead tell us that no human ingenuity, however advanced, is ultimately a match for the planet's raw power? The ruins stand as a monument to both their brilliance and their vulnerability, a reminder that the stones were shaped not in a vacuum, but in a dynamic and often unforgiving world. These angles are not approximately right, they are perfect. One of the most quantifiable and staggering aspects of Puma Punku's stonework is the absolute precision of its geometry, visible in the flawless 90-degree corners and the optically flat surfaces of its andesite blocks. To stand beside one of these stones is to confront a level of exactness that feels alien in an ancient context. Researchers using modern digital measuring tools have documented surface flatness with deviations of less than 0.5 millimeter over a distance of 1 meter. To grasp what that means, consider a standard school ruler, which is about 1 millimeter thick. The variation across a surface larger than a kitchen table is less than half the thickness of that ruler. In the world of modern manufacturing, this is a tolerance associated with machine shops and precision grinding, not with stone blocks shaped over 1,000 years ago. Metrology specialists, the scientists of measurement, point out what this level of flatness implies. Achieving such a plane over a large area is not something you can do by eye or by feeling the stone. It requires a reference standard, a known flat surface against which you can check your work. In a modern workshop, this is a granite surface plate, a slab ground to near perfect flatness used to calibrate other tools. The builders must have possessed an equivalent, perhaps a massive, carefully leveled stone slab that served as their master reference. Furthermore, they needed a method to detect minute deviations from that perfect plane across the entire surface of a block. This could have been a simple but brilliant tool like a water level, where the constant surface of water in a trough shows true level, or a sighting tool that uses the principle of light in a straight line to check for dips and rises. The creation of perfect right angles follows the same rigorous logic. A 90-degree corner is the fundamental building block of modular design. If every block has perfectly square corners, they can be arranged in endless combinations, their sides aligning seamlessly to create straight walls and stable foundations. Any error in the angle, even a slight one, compounds as you add more blocks, causing walls to lean or joints to gap. The perfection seen at Puma Punku tells us the builders understood this principle of cumulative error and eliminated it at the source. The purpose of this obsessive precision was profoundly practical. A perfectly flat surface ensures stable weight distribution. When one massive block sits upon another, any high spot or hollow creates a point of intense pressure, a weakness where the stone can crack under the enormous load. A uniformly flat interface spreads the weight evenly, allowing the structure to bear incredible loads and withstand the test of time and tremors. You can demonstrate this with a simple, illustrative thought experiment. Take a precision machinist straightedge, a tool known for its flawless edge, and place it against one of these ancient surfaces. Then, try to slide a thin metal feeler gauge, perhaps only a few hundredths of a millimeter thick, into any gap between the straightedge and the stone. On many of Puma Punku's blocks, you would find almost no gap at all. This tangible evidence forces a reflective question about the building process itself. What quality control did they employ? After a team spent weeks or months shaping a block, how did they verify it met the exacting standard before it was put into place? There must have been a final inspection, a ritual of measurement using their reference tools, where the master builder gave approval. This step transforms the work from construction into a form of ancient manufacturing, with a clear pass or fail criteria based on measurable precision. This microscopic view of angles and surfaces strips away the scale and mystery, reducing the achievement to a cold, hard numbers game. And in that game, the builders of Puma Punku were playing by rules we thought were invented millennia later. The hardness of the stone forces us to ask an equally hard question about the tools. We know the Tiwanaku culture worked with bronze, a strong alloy of copper and tin, but could they have possessed something even harder? Metallurgists who study ancient Andean technology provide a clear but fascinating boundary. There is no evidence for the smelting of iron from ore anywhere in the pre-Columbian Andes. However, they did have access to one extraordinary source, meteoric iron. This metal from the stars, rich in nickel, falls from the sky in a naturally alloyed state, already incredibly hard and capable of taking a sharp edge. Artifacts across the Americas, including a few beads and small ceremonial objects, prove ancient cultures recognized and valued this rare material. The pivotal question then becomes one of application, not just possession. Could a master craftsperson have taken a small, precious piece of this celestial metal and fashioned it into the tip of a cutting tool or the edge of a drill bit? Theoretically, yes. Using a technique like lost wax casting, they could have mounted a sliver of this super-hard metal into a bronze or copper handle, creating a composite tool with a cutting edge far superior to anything made of bronze alone. Such a tool, even if only a few inches long, could have acted as a master blade, guiding an abrasive slurry to make cleaner, deeper cuts in the andesite. Yet this compelling idea crashes against a wall of silence in the archaeological record. Not a single tool fragment of hardened steel or meteoric iron has ever been found at Puma Punku or in any Tiwanaku workshop context. If these were the secret instruments behind the precision, their total absence is baffling. tools of such value would have been curated, repaired, and passed down through generations of artisans. Their disappearance would need an explanation as dramatic as the site's destruction itself. A more grounded comparison comes from ancient Egypt, where we have clear evidence of how hard stone was worked with softer metals. Egyptian artisans used copper saws, not to cut the granite directly, but as a vehicle for an abrasive. They would load the groove with a slurry of quartz sand or, even more effectively, crushed corundum, a mineral harder than quartz. The copper saw, pulled back and forth by teams of workers, did not cut the stone. The abrasive particles in the slurry did. The copper was simply a carrier wearing away itself in the process. This method works as demonstrated by modern experiments, but it is achingly slow and consumes vast amounts of both metal and abrasive. It could explain the cuts, but it struggles to account for the flawless surface finish and the sheer speed implied by the site's scale. So we circle back to the reflective core of the enigma. If the Tiwanaku possessed a secret toolkit of advanced metal alloys, where did it all go? A culture capable of such sophisticated metallurgy would leave behind slag heaps, furnaces, molds, and failed castings, the inevitable debris of experimentation and production. That evidence is missing. This absence pushes us toward a humbler, yet in some ways more intriguing, possibility. Perhaps the true breakthrough was not in the tool material, but in the system that guided it. Maybe the genius lay in a perfectly rigid wooden frame that held a simple bronze blade or a quartz crystal in an unshakable position, or in a mechanical advantage system that provided consistent, immense pressure for days on end. The tool itself might have been ordinary, but the machine that wielded it was extraordinary. The material of the cutter may be less important than the intelligence of the cut. The scattered precision of Puma Punku gains new meaning when we step back. Seen from above, the site is not an isolated ruin, but a deliberate component in a grander design, one piece of a vast ceremonial complex that included the main Tiwanaku city less than a mile away. This perspective shifts the mystery from a single building to an entire engineered landscape, a sacred geography where every structure played a specific role. Archaeologists who study ancient urban planning describe Puma Punku, whose name translates to door of the puma, as likely serving as a monumental gateway or an elevated platform reserved for the highest elite. Its staggering stonework, then, was not just for show, but a physical declaration of status and sacred function, marking a threshold between the mundane world and a space of profound ritual. The machined blocks we find today may have formed only the indestructible skeleton of the complex, the robust foundations, load-bearing walls, and ceremonial portals that supported grand halls, roofs, and facades made of wood, thatch, or adobe, materials that returned to the earth long ago. Imagine a modern concert hall with its flawless concrete and steel framework, designed to support intricate lighting, sound systems, and seating. The framework alone is a feat of engineering, but its true purpose is only realized when the entire system is complete. Puma Punku's stonework was that perfect framework. Surveys of the area reveal this intentional integration. Broad, carefully leveled avenues and expansive plazas once connected Puma Punku to other key monuments like the Akapana Pyramid and the Kalasasaya Temple, creating a processional route through a landscape of power. The precision of its construction ensured it could bear not just physical weight, but the symbolic weight of ceremony. A powerful parallel exists in the Acropolis of ancient Athens. Visitors today see the majestic marble columns of the Parthenon, but those columns rest upon a massive, precisely cut limestone platform, the foundations painstakingly leveled to create a stable base for the temple above. That foundational work, often overlooked, was essential to the structure's grandeur and longevity. At Puma Punku, we are largely looking at that foundational platform, the impeccably crafted base upon which a magnificent and now vanished superstructure once stood. This integrated view prompts a deeper question about the ceremonies themselves. What rituals or functions demanded such an unshakable, geometrically perfect stage? The answer may lie in the need for permanence and order in the face of cosmic forces. If the site was used for enacting myths, coronating rulers, or observing celestial events, the architecture needed to be a flawless mirror of the stable heavens, a sacred machine where every element was in its divinely ordained place. The robustness of the stone foundations suggests ceremonies involving large gatherings, processions, or perhaps even symbolic journeys that required a durable, enduring path. Seeing Puma Punku as one piece of a larger whole transforms it from a collection of mysterious blocks into a coherent statement of cultural intent. Its precision was not an end in itself, but the essential first step in creating a portal to the divine, a permanent anchor for beliefs that shaped an entire civilization. The air itself was a silent adversary in this high place. At over 12,000 feet above the sea on the Bolivian Altiplano, the environment imposed a brutal reality on every aspect of life and construction. The atmosphere holds only a fraction of the oxygen found at sea level, making even simple physical exertion a test of endurance. For the builders of Puma Punku, this meant that the monumental labor of moving and shaping stone was conducted under a constant physiological strain. High-altitude archaeologists who work in similar conditions describe a world where every task demands more time, more rest, and more careful management of human energy. A worker swinging a heavy hammerstone would tire in minutes, needing frequent breaks to recover. This fundamental constraint reshapes our understanding of the project's timeline and logistics, suggesting that the workforce was likely rotated in shifts, and the construction calendar was dictated as much by human stamina as by the seasons. Yet, this same punishing environment became an unexpected ally in preservation. The Altiplano is a land of extremes, with intense ultraviolet radiation from the sun during the day and freezing temperatures at night. This dry, cold climate acts as a natural museum. The lack of consistent liquid water and the minimal biological growth like moss or lichens have left the andesite surfaces remarkably clean and unweathered. The sharp edges of the cuts, the crispness of the ports, even the subtle polish on some slabs, have survived the centuries largely because the environment is so inert. It is a profound irony. The very conditions that made building so difficult also protected the evidence of that building for us to find. This leads to a fascinating technical consideration about the stone itself. In an environment with such drastic temperature swings, from searing daytime sun to deep nighttime frost, rock undergoes significant expansion and contraction. For a stonemason, this could be turned into a tool. Some researchers theorize that builders might have used thermal shock as part of their process. By heating a section of the hard andesite with a focused fire and then rapidly cooling it with water or even ice collected from nearby peaks, they could create controlled fracture lines, making the initial rough shaping of the massive blocks more manageable. The cold could also have played a role in finishing. Using ice as a flat reference surface for checking the planarity of a stone, or employing frozen abrasive slurries in a more controlled grinding process, are speculative but plausible adaptations born directly from the environment. The builders did not just work in this landscape, they learned from it and used its properties. Their choice of andesite quarried from the local volcanic peaks meant they were not importing an unfamiliar material, they were mastering the very bones of their homeland. This intimate knowledge would have included understanding how the stone behaved in the cold, when it was most brittle, and when it could be worked most effectively. Construction likely followed a seasonal rhythm, with the heaviest labor planned for the drier months when transport across the clay plains was possible, and finer detailing perhaps reserved for times when workers could sustain focused effort without the added hardship of rain or sleet. So we are left with a reflective puzzle framed by the sky. Did the relentless harshness of the Altiplano force a faster, more desperate innovation, pushing human ingenuity to its absolute limit to overcome a world that seemed set against them? Or does the added layer of physiological and environmental difficulty make the precision we see even more statistically improbable, a victory that seems to defy not just history but basic human biology? The environment does not simplify the mystery, it deepens it, presenting the achievement not as an abstract feat of engineering, but as a tangible, breathless struggle against the elements, won by a people who refuse to let the thin air thin their ambitions. The possibility of a shared blueprint whispers across the ocean. Beyond theories of lost local technology lies another controversial but persistent idea, that the builders of Puma Punku were not working in isolation, but were part of a web of ancient global contact. This perspective, known as diffusionism, suggests that advanced building techniques, or at least the concepts behind them, could have traveled across vast distances through the journeys of seafarers or migrating peoples, seeding similar ideas in disparate cultures. Some historians who study cross-cultural patterns point to intriguing, though highly debated, stylistic echoes. They note the recurring use of polygonal masonry, the interlocking of massive stones without mortar, and a fascination with astronomical alignment in places as far-flung as Easter Island, Egypt, and Japan. The precision at Puma Punku, in this view, might not be an independent miracle, but a regional expression of a wider, shared architectural language. The most tangible thread in this theory is the legend of Viracocha, deeply woven into Andean mythology. He is described as a tall, bearded figure who arrived from across the water after a period of great darkness, bringing knowledge of laws, agriculture, and construction before departing westward. To some researchers, this is not merely a creation myth, but a cultural memory, a story passed down for generations about contact with outsiders who possessed superior knowledge. Could Viracocha represent a historical figure or a group from a distant shore who influenced local technological development? The idea of transoceanic contact, particularly with skilled Polynesian voyagers who navigated the Pacific using stars and currents, is no longer dismissed out of hand. We know these incredible mariners reached the remotest islands, and genetic studies suggest some contact with South America was possible. Yet, when we search for conclusive proof of a direct technological transfer at Puma Punku, the evidence dissolves. There are no Polynesian artifacts in the Bolivian highlands, no shared tool kits, no linguistic links that point to a teacher-student relationship. The architectural similarities, while fascinating, are often superficial when examined in detail. The precision fitting at Puma Punku is modular and geometric, while the famous stonework of the Inca, for instance, is adaptively polygonal. They solve the same problem, stability without mortar, but with fundamentally different philosophies. An illustrative comparison can be made with the Olmec civilization of ancient Mexico, contemporaries of early Tiwanaku. The Olmecs are famous for their colossal stone heads, carved from basalt with immense skill. Yet their approach was sculptural, focused on creating monolithic art, not on fabricating interchangeable building components. This highlights a key point: parallel development is a powerful force in human history. Different cultures, facing similar challenges of moving and shaping stone for ceremonial purposes, can and do arrive at ingeniously similar solutions independently. The reflective question this raises is profound. Is the human mind, when driven by necessity and spiritual vision, capable of such strikingly parallel innovation across continents? Or does the uncanny resemblance in certain ancient marvels hint at a deeper, perhaps even a single, source of knowledge that was fragmented and lost? The diffusionist theory ultimately challenges us to expand our view of the ancient world from a collection of isolated lanterns to a potentially interconnected network, where ideas, however faintly, might have traveled on the currents of the sea and the routes of trade. It is a reminder that the story of Puma Punku may not be confined to a high Bolivian plateau, but could be a single, brilliant piece in a global puzzle of human achievement we are still assembling. The silent stones of Puma Punku speak volumes about the society that raised them. To create such a complex required more than brilliant engineers. It demanded the total mobilization of an entire civilization. This was a project that would have consumed generations, binding the fate of thousands to the slow emergence of perfect geometry from raw stone. Economic anthropologists who study ancient states point to a fundamental prerequisite: a massive and reliable agricultural surplus. On the harsh Altiplano, this surplus was not a given, it was a hard-won achievement. The Tiwanaku people mastered a system of raised field agriculture, creating grids of elevated planting beds surrounded by canals. This ingenious method regulated soil temperature, prevented frost, and provided consistent moisture, turning a marginal landscape into a breadbasket capable of supporting a large, non-farming population. That surplus was the fuel for the project. It fed the armies of laborers who hauled the stones, the teams of quarry workers, the skilled artisans who performed the precision work, and the administrators who coordinated it all. Without this stable food base, the dream of Puma Punku would have remained just that, a dream. The scale of organization hints at a powerful, centralized authority, likely a theocratic elite who blended spiritual and political power. They would have commanded the labor through a system of reciprocal obligation, where communities contributed work as part of their social and religious duty, perhaps in return for protection, festival food, or spiritual favor. This was not slavery in the modern sense, but a deeply embedded social contract. Managing the human element was a logistical triumph equal to the engineering. Consider the training required. A master stonemason capable of executing those flawless cuts would not emerge overnight. He would have been part of a specialized guild, learning through a long apprenticeship, inheriting guarded techniques passed down from teacher to student. These elite artisans would have been supported entirely by the state, freed from the need to farm. Then there were the thousands of auxiliary workers, housed in temporary camps near the site and the quarries, requiring food, water, and basic shelter to be transported and distributed daily. Coordinating the quarrying at Mount Capia, the transport across 50 miles, and the final assembly at Puma Punku required a communication and management system of remarkable efficiency. A powerful parallel lies in the construction of Europe's great medieval cathedrals. Projects like Notre Dame or Chartres were not built by a single king's decree alone, but by the sustained effort of entire cities. Guilds of specialized craftsmen, from stonecutters to glassmakers, worked alongside donated labor from the community, all organized by the church over decades or even centuries. These cathedrals became engines of social unity and economic activity, defining the identity of the place. Puma Punku likely served a similar role on a grander, earlier scale. It was a societal endeavor that reinforced the cosmic order and the power of the ruling elite, making abstract beliefs visible and tangible in indestructible stone. So we must ask, what did the society gain from this staggering investment? The answer lies beyond mere function. The project itself was the point. It created a shared identity, a collective purpose that transcended individual lives. It demonstrated the power of the gods and their representatives on Earth, and in its perfect, enduring form, it offered a promise of stability and order in an unpredictable world. The economic and social machinery behind Puma Punku reveals not a mysterious lost tribe, but a brilliantly coordinated civilization operating at the peak of its organizational power, channeling the labor of generations into a single, perfect statement meant to echo through time. Perhaps the stones themselves were meant to sing. Some researchers propose that sound or vibration played a role in the creation or function of Puma Punku, venturing into the fascinating field of archaeoacoustics. This theory examines whether the precise shapes and angles of the andesite blocks could manipulate sound waves, not as magic, but as applied physics. Experts in ancient technology point to a persistent idea found in various cultural traditions: the concept that certain resonant frequencies produced by drums, chanting, or specialized instruments could have been used to affect solid stone. The folklore sometimes calls this sonic levitation, but in a more grounded scientific sense, it relates to the principle of resonance. Every object has a natural frequency at which it vibrates most easily. If you can match that frequency with a powerful enough sound wave, you can create intense vibrations within the material. In theory, focused vibrations could travel along a precise line in a stone, potentially making it easier to fracture or separate along that plane with minimal physical force. This would explain the clean cuts and the notable absence of tool marks, as the stone might have been persuaded to break where desired, rather than being ground away. There is, however, a significant gap between theory and evidence. No direct scientific proof exists that such a technique was used at Puma Punku, and replicating it with any consistency using ancient methods remains a monumental challenge. Yet, the acoustic properties of many ancient sacred sites are undeniable. Structures like the oracle chamber in Malta's hypogeum or some Mayan pyramids demonstrate remarkable sound effects, where a whisper in one spot can be heard clearly across a large chamber. This was likely intentional, designed to amplify the voice of a ritual leader or to create an immersive auditory experience that heightened ceremony. At Puma Punku, while we lack enclosed chambers to test, the complex geometry itself could have been designed to channel sound. The flat, planar surfaces might reflect and focus specific frequencies, and the arrangement of the blocks could have created standing wave patterns or acoustic hotspots. An illustrative example from other cultures is the Helmholtz resonator, a cavity in a wall that vibrates at a specific pitch, sometimes found in ancient Greek theaters or medieval cathedrals to enhance certain notes. While not confirmed at this Bolivian site, the principle shows that ancient builders understood and manipulated acoustic phenomena. This leads to a reflective and compelling question. If the Tiwanaku possessed a deep empirical knowledge of sound physics, could that have been another tool in their arsenal? Chanting or playing instruments during construction might not have been solely spiritual but functional, a way to find the resonant note of a stone block to aid in its shaping. The sonic angle offers a non-mechanical explanation for the precision, one rooted in a sophisticated understanding of the environment's unseen forces. It suggests the builders saw the world as an interplay of vibrations, where harmony in sound could create harmony in stone, turning their entire complex into a monumental instrument for both ceremony and perhaps for its own creation. The age of Puma Punku is not written in its stones but hidden in the earth around them. Determining when this complex was built is a scientific puzzle that directly shapes our understanding of its creators, fueling one of the most persistent debates surrounding the site. Mainstream archaeology relies on a method called ceramic typology, carefully studying the styles and fragments of pottery found in the soil layers associated with the foundations. This cultural evidence, alongside radiocarbon dating of organic materials like ancient plant fibers or charcoal from construction-era fires, consistently points to a primary construction phase during the Tiwanaku period, between 500 and 1000 AD. This timeline fits neatly within the known flourishing of that empire, suggesting Puma Punku was its crowning technological achievement. Yet, this consensus is challenged by a different kind of evidence, one written in the geology of the site itself. Some researchers point to the thick layers of sediment that encase the lower halves of the massive blocks. They argue these deposits are the result of a cataclysmic flood, and by dating the minerals within that sediment or analyzing the depth of its accumulation, they propose the site must be far older, perhaps even constructed before the great floods that followed the last ice age, pushing its origin back thousands of years earlier. This creates a stark discrepancy. Is Puma Punku a product of a known, sophisticated civilization, or is it a relic of a forgotten epoch, a precursor culture whose name is lost to time? The debate began in earnest with the work of Arthur Posnansky in the early 20th century. An Austrian engineer fascinated by the site, Posnansky proposed a radical theory. He meticulously measured the alignments of the Kalasasaya temple nearby, suggesting its walls were oriented to different celestial poles than those of today. Based on calculations of the slow wobble in Earth's axis, known as precession, he estimated the complex was aligned to a sky from over 10,000 years ago. While his dedication was profound, modern archaeologists and astronomers have largely dismissed his specific calculations, noting errors in his initial measurements and the flexibility of interpreting such broad alignments. His core idea, however, that the site feels ancient beyond record, continues to echo in alternative research. The central challenge is that you cannot carbon date a stone. The andesite blocks themselves are millions of years old. Scientists must instead date materials linked to human activity at the site. A piece of charcoal from a campfire used by the builders provides a clear snapshot of that moment. But what if that campfire was built among ruins that were already ancient? The geological camp points to the flood sediments as a defining event. If a great flood scattered the blocks and buried them, then the complex must predate that flood. Dating the flood itself becomes the key, and here interpretations diverge wildly. Mainstream geologists might see those sediments as the result of a massive but localized lake surge during the Tiwanaku era, while others connect them to global cataclysmic events from a much deeper past. This leads to a reflective and profound question. If the stones of Puma Punku were shaped not by the Tiwanaku, but by an unknown people millennia earlier, what does that rewrite about the narrative of human civilization in the Americas? It suggests a cycle of rise and fall far more dramatic than our history books describe, with advanced knowledge surfacing, being lost, and later cultures building upon the literal foundations of their mysterious predecessors. The timeline is not just a date, it is the anchor for the entire story. A younger date makes it a marvel of a known empire. An older date transforms it into a message in a bottle from a world we no longer remember, making its impossible precision not just a technical mystery, but a historical one of unimaginable depth. The story of Puma Punku has long escaped the confines of academic journals, finding a vibrant and often controversial life in popular culture. You can find it featured in television specials questioning ancient history, discussed in countless online forums, and presented as definitive proof of impossible ancient technology. This modern fascination transforms the site from an archaeological puzzle into a cultural symbol, a blank slate upon which we project our deepest curiosities and anxieties about human origins. Cultural historians who study this phenomenon note that places like Puma Punku serve a unique function. In an age of rapid technological change, they become mirrors. They reflect a contemporary unease, a whispered question about whether our current path is the only one, or if brilliant knowledge has been lost before. The stones, in their silent perfection, seem to offer evidence of a different past, one that challenges the linear story of human progress we are often taught. This makes them irresistible to narratives that seek to fill the gaps in our understanding with grand, sweeping answers. The most prominent of these is the ancient astronaut theory, which proposes that extraterrestrial visitors provided the technology or direct guidance to build such sites. While this idea is overwhelmingly rejected by mainstream scholars due to a complete lack of empirical evidence, its persistence in documentaries and books is a cultural artifact in itself. The theory resonates because it offers a simple, dramatic solution to a complex mystery. It replaces the hard, slow work of archaeological deduction with a single, spectacular event. It transforms our ancestors from ingenious innovators into grateful recipients, a narrative that can be strangely comforting or thrilling, but ultimately diminishes their own profound capabilities. Engaging with these ideas responsibly requires a careful balance. We can acknowledge the genuine, unresolved engineering puzzles at Puma Punku, the how of it all, without leaping to unsupported conclusions about the who. The mystery is compelling enough on its own. Consider the difference between two types of documentaries. One might follow a team of archaeologists and stonemasons as they meticulously map the site, analyze tool marks, and experiment with abrasives, presenting each frustrating dead end and small discovery. The other might use dramatic music, speculative recreations of alien visitors, and present theories as near certainties. Both are responding to the same awe, but one prioritizes the method of inquiry, while the other prioritizes the sensation of an answer. This cultural lens reveals something crucial about ourselves. Why does the idea of a lost high technology or an outside intervention hold such powerful appeal? Perhaps it speaks to a longing for a more mysterious world, one not yet fully explained. Or maybe it highlights a subconscious recognition that the conventional timeline of history feels incomplete, that the achievements of past cultures can still stagger us. Puma Punku, in its scattered majesty, has become more than a ruin. It is a story we keep retelling, each version revealing as much about our own time as it does about the distant past. The divide between mainstream archaeology and alternative theory often feels like an unbridgeable canyon. On one side, a rigorous insistence on evidence and known cultural contexts; on the other, a compelling sense that the evidence itself points to something beyond those contexts. Yet the most productive path forward may not lie on either bank, but in building a bridge between them, a synthesis that takes the mystery seriously without abandoning scientific discipline. This approach begins with a simple, powerful admission from within archaeology itself, dismissing the precision at Puma Punku as unimportant or impossible is itself unscientific. A growing number of archaeologists and materials scientists advocate for a new, multidisciplinary investigation, one that brings cutting-edge tools and an open mind to the stones. They argue that the first step is to stop asking whether the Tiwanaku could have built it and start rigorously discovering how they actually did. This shifts the focus from speculation to forensic engineering. The call is for detailed lithic analysis using three-dimensional laser scanning to map every surface and angle with microscopic precision, searching for tool marks too faint for the human eye. It demands controlled replication experiments that go beyond basic copper and sand, testing complex guiding frames, different abrasive mixtures, and the effects of the unique high-altitude environment on the workability of andesite. The goal is not to prove a favorite theory, but to systematically eliminate possibilities until only the most plausible methods remain. History offers a powerful parallel in the Antikythera mechanism. For decades after its discovery in a Roman shipwreck, this corroded bronze artifact was dismissed as an anomaly, too complex to be ancient. It was only when researchers from outside traditional archaeology, including physicists and mechanical engineers, applied X-ray tomography that its true nature was revealed, an intricate astronomical computer of gears and dials predicting celestial events. It was not impossible, it was simply a level of Hellenistic technology that had been completely lost to the historical record. Puma Punku stands as a similar challenge, a piece of material culture that seems to outpace the narrative we have written for its creators. The synthesis, then, is not a single answer but a framework. It proposes that the solution may be a combination of factors we have failed to consider together, a perfect storm of cultural drive, refined technique, and pragmatic innovation. Imagine a society where the spiritual need for cosmological perfection was absolute. This cultural imperative could have funded generations of artisan guilds dedicated solely to solving the problem of stone. Through centuries of trial and error, these guilds might have perfected a suite of techniques, a form of applied knowledge so specialized it was never written down, only passed from master to apprentice within sacred workshops. This knowledge could have included sophisticated measuring systems using water, light, and shadow, rigid guiding apparatuses made of wood and stone to hold tools steady, and abrasive formulas using locally available minerals harder than quartz that we have not yet identified. Perhaps they discovered a way to temporarily soften the surface of andesite using plant-based chemical solutions, a lost pragmatic trick that made the final polishing achievable. This view does not require aliens or Atlanteans. It requires us to expand our view of human ingenuity within a specific, highly motivated cultural context. It asks us to consider that a civilization can achieve a localized technological peak in one area, like precision stonework, without needing to have invented the wheel or smelted iron. The reflective question at the heart of this synthesis is profound. Are we underestimating the innovative power of a culture driven by a unified, sacred purpose? By bridging the gap between skepticism and wonder, we open a path that honors both the stones and the science, seeking answers not in the stars, but in the boundless capacity of the human mind to solve the problems set before it by its own beliefs and ambitions. The final lesson of Puma Punku is not about lost tools, but about the human mind itself. These stones force a quiet revolution in how we view our ancestors, pushing us to discard the comforting but flawed idea that technological progress is a simple, upward climb. Historians of technology offer a crucial correction, reminding us that the word primitive, when applied to ancient cultures, speaks only to the complexity of their tools, not the sophistication of their thought. A society without electricity or steel is not a society without genius. It is a society that solved its problems with a different set of materials and a different kind of wisdom, often achieving results that our own technology, coming from a different direction, finds baffling. Innovation under constraint is perhaps the most powerful engine of human creativity. When you lack a power saw, you are forced to understand the nature of the stone, the physics of leverage, and the chemistry of abrasives on a profoundly intimate level. The builders of Puma Punku operated within severe constraints, thin air, heavy stone, and simple metals. Yet within that box they achieved a precision that feels limitless. This reveals a profound truth. Extraordinary outcomes often spring not from an abundance of resources, but from a deep cultural necessity combined with generations of accumulated, hands-on knowledge. For them, the drive for geometric perfection was likely woven into their spiritual and cosmic worldview. The necessity was not just to build a platform, but to create a permanent, ordered reflection of the heavens. That profound cultural value funded centuries of trial and error, a slow, iterative process where artisan guilds passed down refined techniques from master to apprentice. Each generation learned from the last, correcting mistakes, improving jigs and guides, and discovering which local sand made the finest polish. This was not a sudden invention, it was a legacy of practical knowledge, built one careful cut at a time over hundreds of years. We must confront a humbling possibility that we have lost simple but effective techniques because they were never written down, or because they were so specific to a time, place, and material that they vanished when that culture changed. A powerful parallel is Roman concrete. The magnificent Pantheon in Rome stands under its vast, unsupported concrete dome nearly 2,000 years later, while later medieval builders could not replicate its durability. The specific recipe, involving volcanic ash and a precise mixing process, was a guarded trade secret that faded with the empire, only to be rediscovered by modern materials scientists millennia later. The knowledge was not impossible, it was simply forgotten. What other ancient achievements do we casually underestimate because we have lost the context of their creation, the slow burn of experimentation that led to them? Puma Punku stands as a permanent challenge to our assumptions about linear progress. It asks us to look at the scattered stones and see not a mystery from another world, but a peak of human ingenuity from this one, a reminder that brilliance can flourish in any age, leaving behind puzzles that inspire not because they are alien, but because they are profoundly, magnificently human. The future of Puma Punku is being written not with shovels, but with scanners and algorithms. As our own technology leaps forward, it offers a new generation of tools to finally listen to what the ancient stones have been trying to say. This is the promise of non-invasive archaeology, a field dedicated to seeing without touching, mapping without digging, preserving the very mysteries it seeks to solve. Scientists now arrive at the high plateau with equipment that seems borrowed from science fiction, wielding ground-penetrating radar that can peer meters into the earth to reveal buried foundations or hidden chambers without moving a single grain of soil. They deploy three-dimensional laser scanners that spin silently, capturing every groove, angle, and imperfection on the surface of a fractured block, creating a digital point cloud accurate to within a fraction of a millimeter. This data is more than a map, it is a perfect, permanent record, a snapshot of the ruins as they are today, which can be studied endlessly by researchers across the globe. Imagine the power of this. A specialist in Tokyo can examine the microscopic striations on a virtual H-block, while an engineer in Berlin runs stress simulations on a digitally reassembled wall, all without anyone setting foot on the fragile Altiplano site. One particularly transformative technique is photogrammetry. By taking hundreds of overlapping photographs of a stone from every conceivable angle, powerful software stitches them together into a photorealistic three-dimensional model. This allows for the virtual manipulation of these multi-ton blocks, a process that would be physically impossible today. Researchers can digitally test fits, rotating and slotting the scanned components together like pieces in a cosmic puzzle, to propose the most likely original configurations of the complex. The goal is a grand digital reconstruction, a virtual Puma Punku that stands whole once more, revealing the architectural intent that has been obscured by centuries of scattering. Beyond shape, new forms of material analysis probe the stone's very essence. Portable X-ray fluorescence devices can be held against a surface to instantly reveal its elemental composition, searching for trace residues that are invisible to the eye. The dream discovery would be finding microscopic traces of a foreign material embedded in a cut, perhaps a sliver of a metal alloy harder than copper, or the unique mineral signature of an abrasive slurry from a specific quarry. Spectrometers might detect the faint chemical ghosts of organic binding agents, offering concrete evidence for or against theories of geopolymer casting. Each scan, each spectral reading is a question posed directly to the stone, and for the first time we are developing the vocabulary to understand its answer. Experts in this field express a tempered excitement. They note that technology provides data, not narrative. The lasers will tell us the exact dimensions of a port, but not who made it or why. The radar may reveal a hidden void, but not the ceremony that took place within it. The true work remains the human work of interpretation, of weaving hard data into the rich tapestry of Tiwanaku culture and Andean cosmology. This leads to a pivotal and reflective question for all of us watching this mystery unfold. What will the next decade of research reveal, and are we, as an audience captivated by the grand and the unexplained, prepared to accept answers that may be surprisingly simple? The most likely breakthrough may not be the discovery of a crystal power source or alien alloy, but the gradual accumulation of evidence for a highly refined, yet entirely human, technological process. It might show us a suite of clever wooden guiding frames, a locally sourced abrasive mineral of exceptional hardness, and a social organization capable of sustaining precision work for generations. Such an answer does not diminish the wonder, it redirects it. It places the genius firmly in the hands and minds of the people who lived there, who looked at a volcanic mountain and saw not an obstacle, but a canvas for their vision of cosmic order. The future of discovery at Puma Punku is therefore an open and profoundly exciting chapter. It is a collaboration across centuries where 21st century sensors seek to decode the language of 15th century craftsmanship. Each new scan is a conversation with the past, and we are only now learning how to listen. The scattered stones of Puma Punku do not whisper a single, easy answer. Instead, they resonate with a chorus of questions that have echoed across our journey together. We have walked the lines of their razor-thin seams, felt the impossible flatness of their surfaces, and traced the complex geometry of their interlocking forms. We have weighed the theories from masterful traditional methods and seismic genius to the haunting possibility of a forgotten innovation, each one a testament to the human drive to explain the extraordinary. The labyrinth of this mystery has no final chamber, no plaque that declares the secret solved, and perhaps that is the most important lesson of all. The ultimate takeaway from this high plateau is not a verdict, but a posture, a humble acknowledgement that our historical narrative still contains profound and silent gaps. Puma Punku stands as a permanent corrective to arrogance, a reminder that the past is never fully known, only continually rediscovered. It challenges the linear story of progress, showing us that ancient cultures could achieve localized peaks of sophistication that still stagger our modern imagination. Whether the answer lies in a yet-to-be-understood refinement of known tools or in a school of knowledge that faded with its masters, the result is the same, a monumental achievement that pushes the boundaries of what we believe was possible. This ancient puzzle, therefore, serves a vital purpose in our present. It is a masterclass in balancing wonder with rigor. It encourages a boundless curiosity, the kind that looks at a machined stone and dares to ask how. Yet it also demands disciplined inquiry, the slow, careful work of measurement, experimentation, and context that separates storytelling from understanding. The true value of a place like Puma Punku may not be in proving one theory definitively right or wrong. Its gift is the conversation it sustains, the questions that keep us looking closer, thinking deeper, and respecting the ingenuity of those who came before us. It invites us to hold space for mystery without surrendering to myth, to marvel at the artifact while honoring the culture that created it. So as we leave these stones to the wind and the thin Altiplano sun, consider this: the greatest enigmas of history are not locks to be picked, but lenses through which we examine our own assumptions. What other chapters of the human story might we have misread because we underestimated the creativity of our ancestors? We would love to hear your own reflections on this timeless puzzle. What theory resonates most with you, or what detail from the site leaves you the most curious? Share your thoughts in the comments below, and if you enjoyed this deep dive into a past that challenges our present, subscribe for more journeys to the edges of history's greatest mysteries. Thank you for exploring.